So sorry for the delay this morning. Obviously, a little bit of time to go out and get some coffee and refreshments, but we're going to get going now. So the first presenter this morning is Mr. Glue. Over to you. Give my hand.
Good morning, everyone. Pleasure to be here today to share my work with you. My name is Al-Roomi. I'm a PhD student under supervision Dr. Al-Roomi. And I will talk about my work under the topic robust fuzzy logic controller, a green plug switched filter for non-linear nodes. The outline of the work presentation is the abstract and the introduction, system description, and the road case, and simulation result, conclusion, and then future work, and finally the references. The abstract of the work is that to create a new design filter, and we use it for the non-linear loads, and this and we give to this filter name as a modulated filter, capacitor compensation for the switches filter compensation, and we'll use this filter across of this source. The introduction of the topic is the fact-based, modulated filter capacitor compensation for the switch filter compensator. And this is the a member of the family of the green plug filter compensation scheme, and use this one for the voltage and the current and the power quality enhancement, and the efficiency power utilization. Also, we can use for the model pre-design, and we use expert knowledge. The system description for the single-phase electric utilization system. We have here the source and the transmission line and the load. When they runs the system with we expect the load is linear, so the harmonic will goes directly to the filter, and the filter will get the signal from the controller, which will use the fuzzy logic controller. And this is the filter, the structures of the filter, which is consists of the two sectional parts, which is the switch and the switch and the rectifier. Yeah. When we use the non-linear load, as you see here for the linear load, the harmonic will goes through the linear load, and there is no control for the harmonics. When we use the non-linear load here, you see the blue arrows, that the harmonics will transmission line and then goes through the filter, the design filter, and the fuzzy logic controller will give the signal to the switch to open and activate it, and then the filter will work and will absorb the harmonics. This is the structures of the modulated filter. This is the system description of the fuzzy logic controller. We have here the system consists of three parts. The first part is the fuzzification, and the second part is rule base, and the last part is defuzzifications. And then we have the system here. The system will operate the actual signal, which is the system output here, and we have here the reference signal. So we'll compare, between, and we'll go to the fuzzification case, and yeah, this is the data, the output of the actual and reference signal. We go to the fuzzification system, and then the rule base. The rule base will receive the data and will operate the system. So the basic operator for the rule base that we keep our system in zero phase, in zero line, and then the fuzzification will receive the data from the rule base, and then we do the fuzzification of it, and then the data goes to the system. From the data, the defuzzification data will goes to the system and will continue the operation. Here the rule base, we have the matrix here, and the diagonal line is the zero. This is the zero base, the zero line for the system. And we have here the positive, the big positive, or the positive big for the signal, and the positive small, So the criteria of the rule base to keep the system in zero line, and and we have here the negative big and negative small. So on the same, the other side of the matrix will sort to the line, the zero line. For the result here, we have the RMS voltage and current, and the power quality and the power factor values at the source side, with nonlinear or under nonlinear load irrigation, with modulated filter, capacitor compensation, switch filter compensation device. As you see here, the power the power quality and the power here, and okay, variation with the time. Also the voltage will stay in 1, which is the acceptable result, and here the power factor, also the power again here. Disarms voltage and current, power quality, and power factor values, AC load. This is the result at the load, and with nonlinear load verification with the modulated filter. For the current, for the filter and capacitor under nonlinear load variation with the designed filter, here we get the sine wave for the current, which is acceptable to use. Here we have the frequency spectra at the source and at the load here. When we use the filter, the switch is activated, will absorb the harmonics, and if you see here, when they start at the source, there is the harmonic here. When we use the filter, this is at load side, the harmonics little under this level, which is acceptable and good result, and the voltage here is less than 0.2, which is acceptable for the system at the load side. In conclusion, we found that the filter modulated the capacitor compensation switched filter compensator is useful to get the good result and remove much the harmonics to improve the power. Improve the power utilization, and we can use this filter to the other scheme like three-phase or and we use in this. We use in this topic the simulation Simulink in MATLAB. For the conclusion to the SFC, the green plug-based filter compensator scheme is very useful, as I said before, and the loads and smart grid distributed and renewable energy interface scheme, and the harmonics, reduction task, and the power quality and power factor, also the efficient electric utilization. In future work, here on this paper, we use only the nonlinear loads, and in the future, or the other work we did in different loads, like arc and DC motor and other stuff for the different loads, and we get result, and just we submit it to IEEE. Also, we now I'm working on the three-phase system instead the single-phase system, and create the new design for the filter and use with different lodestone. This is the reference. Thank you.
So, we're running a little behind, so I'm going to limit things to 2 questions. Go ahead.
The harmonic.
Yeah.
Yeah, this one.
Yep.
So on the left-hand side, you said that your frequency is
Yeah, this
the
one.
original frequency, right?
Yes, in this. Yeah, in source.
And the right-hand side is that
In the low side.
So you reduce the harmonic in the lower frequency, but at higher frequency you also have introduced a huge spectrum. Would that require another filter? Because if from your slide, the left-hand side, you didn't have that harmonic. Now after your filter, we have a massive spectrum, so
Yeah.
that has to be addressed, right? So that would translate to sending a lot of harmonic to the grid, like conduction harmonic.
Yeah.
Would that require another filter or just?
Yeah, you see, you cannot remove all the harmonics. So we designed this filter, as you see the result, it's better than the result of the source side here. And yeah, this is, acceptable result of the system. And the system will operate like it.
So what is the acceptable limit in terms of EV in your system?
Yeah, so this one is not like, big harmonic to have this system. This is acceptable.
Next question? All the way back. I'm going to walk, okay?
Can you go back to the fuzzy logic controller slide? Yes. So what are
Here.
M1 and M2 and
What?
What are M1, M2 and M3? And how you determine those?
Okay. So M1 and M2 and M3, this is the gains, and we find them online tuning in the system.
Okay.
All right, go ahead. So our next presenter is Mr. Gamma Ali.
Hello everybody, my name is Gamma Ali. In this presentation I'm going to talk about biomass energy in heating and electricity generation. This presentation includes introduction, our heat production sources, energy use, and household energy use in Canada by province, challenges of fossil fuel energy resources, forced biomass energy, the future for electricity in Nova Scotia, opportunities, and future work. Even though we consume a lot of electricity in our daily life, future projections indicate that the consumption of electricity and the power will increase. According to World Bank data on electricity usage, Canada is one of the highest per capita consumers of electricity at over 16 megawatt hour. Canada's consumption is greater than Japan and Germany combined, and is exceeded only by Norway and Iceland. In Canada, we usually produce electricity from coal, natural gas, nuclear, oil, hydro, wave and tidal, wind, and eventually from biomass. Even though Nova Scotia hasn't a nuclear facility, nuclear plant, it is grid connected to nuclear plant from New Brunswick through transmission line. The biomass is an organic matter like wood, and wood waste can be burned to generate electricity. This chart shows us the energy used in Canada 2010 by province in metajoules. According to Statistics Canada, the consumption or the demand is increased by 3.6% in 2000 compared with 2009. In this chart, Ontario has the peak demand at around 2,400 petajoules, followed by Alberta, then Quebec. Nova Scotia has around 150 petajoules in demand. 1 petajoule is enough to supply the Montreal metro for a year. This chart shows us household energy usage in gigajoules. Here in Nova Scotia, electricity was 39 gigajoules, the oil was 64 gigajoules, wood and wood pellets was 99 gigajoules, and the propane was 9 gigajoules. The challenges of fossil fuel energy resources. They have higher prices in addition to the health and environment impacts that will affect people and the environment. Annual global energy. According to some researchers, there is an annual increase in biomass consumption from 0.6 to 2.3% until 2030. The predicted renewable energy in 2012 was 19%. 9% of them was from biomass consumed as cooking and heating. Meanwhile, the consumption of electricity from biomass is still very low at 1.8%, compared with wind energy at 2.9%. The electricity generation biomass facilities in the maritime in 2013. Nova Scotia has 2 biomass facilities in Port Hawkesbury and Brooklyn with total capacity of 90 megawatt, which contribute in 4% in Nova Scotia's electricity. Meanwhile, Newfoundland produced 159.6 megawatt in 4 biomass facilities. Electricity generating facilities in Prince Edward Island burns a combination of waste wood and oil, but doesn't currently have fossil biomass electricity capacity. Biomass as energy source. We burn the biomass, the chemical energy is released as heat. The wood we burn in our fireplaces is a biomass fuel. The byproducts of this biomass fuel is carbon dioxide and ash. The carbon dioxide can be consumed by plants or absorbed by plants, and the ash is consumed as fertilizer in the farmers. The future for electricity in Nova Scotia. Nova Scotia has one of the few tidal wind energy in the world with 20 megawatt capacity, and as of 2015, they installed 350 megawatt wind energy, and under its 2010 renewable electricity regulation, Nova Scotia is committed to obtain 25% of its energy from renewable energy sources by 2015 and 40% by 2020. The opportunities of biomass and renewable biomass specifically as energy source. It helps in finding job for local. It affects positively the health and environment, which is reduce the carbon dioxide and other benefits, in addition to economic benefits. As a PhD student, I am currently in the searching and collecting data phase. When I am done with my gathering information, I'm going to search in using smart grids for efficient utilization of biomass fuels, whereby smart grids can be deployed to solve techno-economic problems and many other problems as well, with efficient and sustainable utilization of fossil fuels. That's my presentation for today, and this is my reference. Thanks for your consideration.
Questions? No questions? No question?
So can you define what is the biomass? Does it include the garbage that we have?
Say it again, sorry.
I mean that when you say biomass,
Yes.
has to be trees and plants and all the organics materials.
Okay, let me go to the definition. Biomass is anything that is or has once been alive. Logs, cows, trees, plywood, cotton, and everything is considered to be biomass.
So how do you get them? Where do you get them?
Depend upon the facility. If you use wood just from forests, if you use corn or sugar cane, there are different types of biomass resources.
I'm just wondering a little bit of the last here. Could you briefly describe new results there? Summarize.
Actually, there is no results. I'm just introducing the biomass because I am, as I mentioned, in the searching phase. I am collecting data now to do my research on this topic.
Oh, so it's a literature review.
Yes.
All right, thanks.
Thank you. We'll put them ahead and then we'll move on. Our next presenter is Mr. Park.
Okay, well, good morning, everybody. My name is Kyle Park. I'm a student of Dr. Kata's, and today I'd like to introduce to you the topic of my research, which I've decided to title Properties and Applications of the Prolate Spheroidal Wave Functions. Brief overview of how I intend to present today is a fairly standard format. I'll be introducing the topic of my research, my motivations for why I'm choosing to study it. From there, I feel it necessary to do something about a mathematical preliminary or background to justify some of the rather lofty claims I make for the functions later on. We'll be discussing an application, possible application, some preliminary results, and then go on to give a rather abridged list of my sort of research directions and future works, and then open the floor to questions. So, to begin, what are the prolate spheroidal wave functions? Well, they are a family of mutually orthogonal band-limited functions that are the solution to the following differential equation, itself titled the prolate spheroidal wave equation. It arises from the solution of the standard Helmholtz wave equation upon its conversion to the prolate spheroidal wave function. If you want to have an idea of what they might look like, just so this doesn't seem completely out of left field to you, they qualitatively look similar to Bessel functions, specifically the spherical Bessel functions, which shouldn't be too surprising considering they arise from the same wave equation upon translation to the spherical coordinate system. In around the 50s, a researcher defined a particular normalization technique for these prolate spheroidal wave functions, and in doing so, defined a related set of functions that we in our group have come to term the linear prolate functions. We use the letter psi to represent it here. And as you can see, it's simply scaled by the amount of energy in the function within a certain interval, the eigenvalue associated with the function, which I'll be addressing shortly. And as it turns out, for a function written this way, a selection of a free parameter c greater than 0, the lowest order member of this family has actually got a rather special property amongst all band-limited functions. It has the best energy concentration. It's the most compact concentration of energy, of any function possible. And that bandwidth is related to C and the interval of analysis T naught using the relationship depicted below. My motivations, besides this sort of band limiting property and energy concentration property, though these facts sort of lead into the future properties that I'm more interested in, these LPFs do have some properties that would make them very attractive for use in, let's say, interpolation and extrapolation theory, as well as in signal processing in general. Moreover, our group has a particular proprietary and robust technique for actually generating these functions. Much of the state of the field of research into this class of functions is focused on being able to reliably generate these functions and the tricks of numerical methods that it takes to know some of these functions in some locations on the real line. Fortunately for us, we have sort of are one step ahead of the game in that regard. And therefore, what I would like to expand on isn't the theory of generation of these functions, as is very common, but rather the theory of putting them to use. So here's just a quick picture mathematical preliminaries then. So I mentioned that these functions have eigenvalues associated with them, and it turns out that in proving that these have this energy concentration property, the researchers connected the fact that it is a solution to that differential equation to an auxiliary problem about the so-called sinc kernel eigenvalue problem. So it turns out that the eigenvectors or eigenfunctions to this problem are the LPFs that I've been talking about. Now, the fact that these linear prolate functions are the solution to this sinc kernel eigenvalue problem imparts some additional properties. So the LPFs are orthogonal on the L2 norm over the infinite interval. That's not a unique property, by the way, so if we take the inner product defined in the standard way, we'll find that the inner product is only non-zero if we are sort of integrating the same function with itself. However, the LPFs are also orthogonal over a finite interval norm. Again, this isn't a unique property in and of itself. Cosine and sine have this property, for example. But the linear prolate functions are the only functions that have both of these properties simultaneously. Now, taking that into account and extending this orthogonality property in the same way that we do by analogy to the Fourier series, we could define a similar sort of orthogonal expansion, introduced here, named after the researcher, the primary researcher, into these functions. The Slepian series is an infinite series that can represent any band-limited function f of t exactly as a sum of coefficients multiplied by the linear prolate functions, where these coefficients are obtained through essentially the inner product of the original function with the linear prolate function. You'll notice that there are actually two forms of the analysis equation here. One over an infinite interval, one over a finite interval. So as we do with other sort of infinite series, if we want to make some sort of an approximation, because practically speaking you cannot ever use an infinite number of terms unless you're doing purely analytical work, we could approximate any band-limited function or any, let's say, nearly band-limited function using a truncated form of the series. So we could say with n plus 1 terms, a function could be approximately represented as a partial series, if you like. Now, for approximating a function like this within an interval, minus t naught to t naught here, it turns out that only a finite number of coefficients are needed. It's been empirically shown that the number of coefficients that you need for n, what n needs to be, the highest order coefficient, needs to be 2c over pi rounded up. So as you can see here, we have a sample function, a test function if you will, sampled at 20 points of the function cos 10t e to the minus pi t squared, so a Gaussian with a cosine, or a cosine with a Gaussian envelope. You'll notice that, that the number of coefficients needed to get the blue reconstruction curve is only 10, whereas the formula I just presented is roughly 2/3 of c. So n is less than that, but mind you, that is a sort of upper limit. In this particular case, since cos and the Gaussian function are both even functions, the odd indexed linear prolate functions themselves have odd symmetry, so their coefficients. So we get a very good reconstruction of the original function with only a finite number of terms. Now, here's where some of my preliminary work comes in. So suppose we consider those sample point, those sort of discrete data points to be sampled points of a signal at some sample rate fs. If we have m sampled points and we need n plus 1 coefficients to have a good approximation of this function inside the interval, then we could, let's say, reduce the total amount of data we need to keep in order to fairly represent the function inside the interval. So I define a sort of ratio here to express what level of compression we seem to get. So clearly, if eta is less than 1, then our decomposition leaves us with less data than what we started with. And what I've noticed here is that by simply plugging in our sort of known values of C and simplifying our formula, and realizing that if we have m samples, that this also has an expression in terms of the parameters of the problem that we've already presented, it turns out that our ratio eta can be expressed rather simply, as if we drop the rounding as well, by the way, it's just sort of a proper asymptotic case for rather large numbers. It turns out that our ratio is actually an expression of Nyquist criterion. So in other words, the approximation becomes good when the number of terms in the series begins to agree with sampling theorem. So that tells us that, well, if we're going to try to compress it this way, compress data this way, it would be no better or worse than a intentionally truncated or fully kept Fourier series in terms of compressing data. But some interesting things happen when we consider the effect of taking these coefficients, both for the Slepian series and Fourier series, and using them for upsampling, interpolating, if you will, analogous problems. So, on the left, we see the picture previously. On the right, we see the original function as well as a Fourier series reconstruction. So taking the Fourier series coefficients and using that to upsample those basis functions with the same coefficients in order to interpolate the signal. And while it doesn't appear so well on this image, we can zoom in quite well here and notice something rather striking appears. In the sense that it is a good approximation, on the left, the Slepian series actually better reconstructs the function inside the interval than a Fourier series using exactly the same amount of data. As you can see, the red curve is the original function on the right-hand side, and the blue curve is the recovered or reconstruction function using only sines and cosines in the Fourier series. The character at the ends of the interval changes quite significantly. The curvature and slope both change and start to deviate from the known function as you get closer and closer to the ends of the interval. So this is a really striking result to me. And so, where I intend to go with my studies is to investigate this upscaling performance, because this suggests that the Slepian series would be capable of upsampling without introducing high-frequency artifacts, which is rather counterintuitive, I might point out. Beyond that, I'd like to expand on the relationship between the sampling theory and the truncation property, as mentioned, make it perhaps a little bit more rigorous and find out from what both of these properties stem, actually. And beyond that, just in interest of developing the theory even more, I'd like to expand on the errors associated with computing a Slepian series. Is there an error phenomenon that shows up similar to Gibbs error when you use truncated Slepian series instead of a full necessary set of data? And I also have some hunches of some other things this could be used for, but I don't think I'll bore you with that. So, our works here have been cited. I thank you all for listening, and if there are any questions, I'd be happy to answer.
Thank you. Interesting presentation. So I have a question about reconstruction. So can you formulate your result maybe more detailed? Like for what class of functions do you prove that the reconstruction using these functions is actually better than, say, Fourier series? So you are presenting an example,
Yes.
right? And here we have an exponentially decaying function, which is fast decaying. So just like the Gaussian bell shape. Is this result true for a more general class of functions?
That is perhaps what I'm looking to investigate next. For example, something that rolls off rather nicely may perhaps be something of a fluke. I need to rule this out, of course. So it's too soon to say precisely what class of functions these would be best for. However, the analytical background, of course, suggests that they are best for anything that is band limited, or at the very least, approximately band limited.
And then, from the perspective of sampling theorem, in your future work, what do you expect to target in terms of these functions? If you can go to the slide for a relationship between the sampling theory and truncation property, what are you planning to address?
Well, this first is what I meant by this line item here, is to more rigorously develop the claim made in literature that this truncation property that holds whenever it's tested actually holds rigorously true in theory. Right now, this is an empirical formula that's been developed. It's not something that has been, let's say, rigorously enough for my comfort level proven. That's something that I'd like to do so that I actually have a factual basis for future claims that I seek to make.
Okay, sounds good. Thank you.
Hi, again, a very interesting presentation, thank you. I guess a question and comment, which one is it? Border between the question and comment, I guess. Are you familiar with the wavelet theory?
Sorry, I didn't.
Are you familiar with the wavelet theory?
I have heard of it, and I do believe some people study another related set of functions called the discrete prolate spheroidal sequence with respect to wavelet theory. I think there is definitely some overlap between this and that, but it's not a field of study that I've done anything more than a surface level, superficial look into. But I think there are probably grounds for to be made that I perhaps should connect this to wavelet theory.
I think it may be interesting because basically the premise of that theory is that you can, for specific signals, actually to read this question, for specific type of signals, you can choose the proper families of wavelets, which actually need not be orthogonal, that interpolate the best.
Right.
So that might be a prolate spheroidal function, might be a particular case actually.
Thank you for the suggestion.
Yeah, and a quick question, just out, I'm curious, you made a comment, it may not be your result, but probably the classic result, because I'm not as familiar with the prolate spheroidal functions. You made a comment that they are the most energy concentrated set of functions.
I perhaps misspoke in a bit of a hurry. I'll go back to the slide. So, Okay. So, in specific, it is the lowest order member in the picture, let's say, the dominant blue curve on the left-hand side. That would be the zero order linear prolate function. So it's very bell-curved. And there's some other additional properties that I've left out because they weren't extremely relevant. But that function across all truly band-limited functions, meaning in the frequency domain this function has compact support, it's truly zero outside of the stated bandwidth limit. This function has the best energy concentration, period.
Okay. Well, of course you're excluding the delta function, right?
Sure.
Yeah.
I suppose that might be the trivial case that nobody
All
talks
right.
about.
Okay. No, yeah, thank you. Thank you for the clarification.
Yeah.
Thanks.
So I'm going to take one more question. Really want. We're just pointing towards you.
So when we are compressing, when we are comparing different compression algorithms, the first thing is that you should also look at the wavelet function, because the current standard for the compression based on the wavelet that JPEG 1000 is based on wavelet and distributed Gaussian transforms. And my question is, what is the computational complexity of getting the projection of this normal basis function? At what expense this improvement can be? Discrete wavelet transform or discrete Fourier transform?
That is the issue, I suppose, right now. As I've alluded to, the biggest problem that the majority of I suppose the literature is focused on is being able to compute accurately over the entire range of the entire functions. Some people can very accurately get it within the interval that I've discussed. Not many people can get it very far out past the interval. However, nobody has a very, very great way of rapidly computing the functions. There is no fast Fourier transform, in other words. Having said that, a computationally effective approach, one that I'd be sort of looking towards if I were to say license the technology, would be to simply build a library to circumvent the necessary problems associated with having to calculate the functions on the fly. Rather, you load up a library and deconstruct and reconstruct on demand rather than a live calculation every single time. And you want to apply a way of doing this. But to reiterate, no, there is no fast Fourier transform equivalent. And because of that, while I don't have, I can't tell you the exact polynomial order, let's say, that this operation takes, it's not good. So it's certainly not yet ready for some sort of real-time application.
Thank you. That's it for questions. We'll move on. Our next presenter is Mr. Al-Roomi.
Good morning. My name is Brahma. I'm a student of Dr. Kamal working on time domain analog to digital converter. So this is all the agendas, motivation. Then we'll talk about time domain briefly, problem definition, prior state of art, the research that we conducted, just results, and then references and questions. As the name can tell you, analog to digital converter is an interface to take you from analog world to digital representation of that analog quantity. This sort of interface exists in every single device that we carry: phones, laptops, projector, everywhere. Can be used for sensor applications, can be used for medical applications, can be used for MEMS interface, can be used for audio. For example, if you can see this, if you want to record the music, you will first pass it through a mic, then ADC to that disk. If you want to hear it, take it back through a DAC, which is a digital to analog converter, then to mechanical wave, then to a microphone. For medical acquisition systems, if you look to that brain, as we can see, there are analog quantities over there if you want to measure them, so you have to take them from analog to digital and process them in digital domain to get what you want. Also sensing. If you want to sense temperature, you want to sense color, you want to sense any quantity at a sensor node, so you will first sense that quantity, which is basically a sort of analog, take it from analog to digital, sort it, and get it back to its representation. This literature review is basically the effective number of bits over the x-axis, which is the sampling rate, for the previous different types of ADCs. As we can see, there is a trade-off between effective number of bits and sampling rate. If you want higher sampling rate, then that will come at the cost of effective number of bits, lower effective number of bits. If you want higher effective number of bits, that will come at the cost of less sampling rate. So if you look at the sigma delta, which is basically the best in terms of effective number of bits, but it is the lower one, or the lowest in terms of sampling rate. When the time domain methodology comes to the side, this sigma delta improved it to go either better and better and mitigate this trade-off. Basically, if you got to that point, top corner is the best one, but we can go up to either like 1 mega or 10 mega with a reasonable effective number of bits, 12 or something like that. And these are the applications that are dedicated for these types of ADCs. So this is basically, as everyone take undergrad course, the conventional voltage domain ADCs, basically microstraight or oversample. So the same thing will happen for time domain analog to digital converter, either Nyquist or oversampling as well. With this technology shrinking down, so we know 1 micro technology or 0.35, we use like 3.3 volts. But when we go down to 180 nanometer, 90 nanometer, 65 nanometer, we reach 1 volt or either less than 1 volt. So then representing the analog voltage in a voltage domain becomes more and more challenging. So for that reason, we'll go to time domain. And we are lucky that when you go down in technology, with technology shrinking down, the volts will drop, but the switching frequency becomes faster and faster. And that will give us the benefit of representing the signal time domain instead of voltage domain. That means instead of quantizing in a vertical fashion, you will quantize now in horizontal fashion. If you see this, the second figure, you will first go from voltage to time or frequency, then you will quantize in time domain. So the figures of merit for any ADC ranging from, are they compatible with technology scaling down, power consumption, noise area, and cost? Are they synthesizable? That means you write a code, and from the code you will get a product. And the speed. For time domain, which is basically digital in nature, time domain beats voltage domain and almost six figures of merit. So for the speed is, we can say it's natural because it depends on the application, what you want. If you want high speed, that you will sacrifice some of the effective number of bits. If you want low speed, it depends. So the main problem for time domain, analog to digital converter, is when you go from analog, the voltage, to time of the frequency. If you see this figure, the x-axis is the voltage, the y-axis is the frequency, or consider time. So ideally it should be a linear line, but practically it is not. There is a nonlinearity. This nonlinearity will create a harmonics in the spectrum. These harmonics will degrade the output, the ADC performance, because will appear at the output of ADC, degrading the SNDR, signal to noise and distortion ratio. So I'll give you a brief story about when the VCO, analog to digital, come to the site. VCO stands for voltage controlled oscillator. Voltage controlled oscillator comes to the site 1999. At the first has been used inside a sigma delta closed loop, replacing the conventional converter based quantizer. So they used the VCO and then followed by a counter to count the frequency and then feedback to the summing node, and they find out this give them better resolution. However, the nonlinearity still degrade the output spectrum of the ADC. In 2004, Mr. Matthew presented another standalone VCO analog to digital converter without using a counter. Just the VCO going to a frequency by VCO, the analog input going to frequency by VCO, then buffer it to isolate it from a sampler. The sampler will just symbol bank of D flip-flops, sample that phase, then differentiate it in a digital domain using another D flip-flop followed by XO. You will get the representation in digital world of that frequency. To make it a little bit more clear, if you see this is the model. So basically, you have a single tone input goes to this shadow or a gray area box is the model of the VCO. So you will go to frequency domain by changing this analog input to a frequency with the harmonics, and then we will accumulate that frequency to get a phase, and then sample that phase, and then differentiate it. Sampling process or quantization process will create some quantization noise, which will be shaped to high frequency domain by this differentiator. Okay, but still the harmonics generated by this nonlinearity appears at the output of the ADC, which still degrade the output of the ADC spectrum. If we can categorize the solutions proposed to mitigate this problem, can be categorized to closed loop solutions or open loop solutions. Let's have a look to closed loop solutions. The top corner, the top left corner solution comes from IT with two consecutive solutions. First, use a standalone VCO with a phase quantization as a replacement of the conventional quantizer and feed it back. Then they find that measuring the phase, the frequency is not the best way. They find that measuring the phase will combat this problem. So in reference number 8, they just measure the phase and convert it to a reference phase and feed it back. This has enhanced the output SNDR by around 25. If we look to the second figure, the second figure is sort of pipeline ADC. So it's two-step. First you take it, you quantize the VX, which is the analog input, by a flash ADC, and then take it back, and then take the residue to the VCO. So then you have just a small range at the input of the VCO. That means you will have a sort of linear output at the end. The other solution uses the same pipeline ADC architecture inside the signal delta. This will increase one more degree of noise shaping. Instead of one first noise shaping, you will get a second noise shaping. However, this will add more constraints on time domain issues. These are the open loop configurations to solve this problem. So using Zodo differential will cancel the even harmonics. We will lift with odd harmonics. There's an estimation filter to estimate this error and then take it to a lookup table and correct it and get it back. This is a very good one. However, it has a convergence time, and this convergence time sometimes cannot be tolerated, sometimes can be tolerated. The other solution, which is considered as an open loop, is using a pulse width modulation at the front end of the VCO ADC. So at this time, you will have just 2 points to modulate the VCO. Since there are only 2 points must be a linear, because you have 0 and 1, that is it. So you will have 2 points at the frequency domain or time domain, then should be linear. The constraint of this one, the carrier frequency of PWM should be very high to push this frequency at as far as possible from the baseband. Okay? And this will add more power. The other solution converts the voltage to time, then feed it to a CCO, which is current-controlled oscillator instead of voltage-controlled oscillator. And the other open loop solution is to use a replica or auxiliary path of the same VCO ADC to sense this nonlinearity and then use an additional linearizer block to linearize this, the output of the ADC. The main problems of these, for a closed loop, the main problem, timing issues, complexity, and a higher order of filter to get more gain. For some of open loop solutions, the convergence time is the main problem. Sometimes the accuracy is not that much good. So what we did is, with an open loop, when we look at this literature review, we find out that the bottleneck of this ADC is basically the VCO itself. So we have to solve this problem inside the VCO instead of going to another box. So if you look at this ring, start from number 1 to number n, this is the VCO from VCO. And instead of applying the voltage input at all nodes at the same time, we average them through a binary weighted voltage network. So at each time, each one of these blocks will see a different version of the input voltage, and that different version of the input voltage will generate this corresponding frequency or time based on that voltage. So now they are not equal. However, at the output you will get a certain frequency which is proportional to the main input voltage. FDC slice means voltage to frequency to digital converter. So we have this phase of frequency, then we take it to a digital representation by D flip-flops and XOR gates. This is the phase at the output of the VCO is the accumulation. KVCO stands for the gain of VCO and the input and the free running frequency. The digital output representation is 2 by KVCO TS. T is the sampling, time sampling. AN is the amplitude of the input voltage. And the quantization noise Q, it's clearly noise is shaped by first order probability. This is more conceptual illustration. The first figure, figure A, is the conventional one used in every single VCO ADC. So you apply Vn to modulate the frequency. So basically you modulate the time of each single delay element. But because you close the loop, then you will generate that frequency, which is basically 1 over 2n tau d. Tau d stands for the time delay of each delay element. Okay? What we did is average this input through voltage network, through a resistor network. So at each node, the voltage first will go to another version of the voltage, then apply to that delay element, and then generate the time corresponding to that delay, to that voltage, and at the end you will get the frequency. So the obtained expression of frequency now is not the conventional one, it's 1 over 2, the summation of the max Ti minus the summation of the min Ti over n. Okay, Vi is the voltage at that specific node. I stands for the number of the node number 1, node number 2, and so on. And this is the expression of the voltage. This is another intuitive way to explain what's going on. It's an arbitrary node. So this is, the red line is time to voltage characteristic from a 65 nanometer. If we can see, it's a nonlinear, but if we want just a certain type of it, or a certain region of that curve, so look to the number, step number 2. So voltage to the voltage node. So it should be linear because it's just voltage to voltage through a resistor network. Then step number 3, voltage node to time at that specific node, you will get just sort of an inverse, and then spread that voltage from step number 2 to step number 4, you will get the full swing over the time voltage, you will get a certain inverse. This, if you just take it back to frequency, you will get almost a linear with a very small error. These are the results obtained from 65 nanometer. Okay, the number 1 or figure A is the conventional one. The voltage goes from 0 to 1. As we can see, the nonlinearity as high as 100%. Then P is the binary weighted from 0 to 1, 2, for the nonlinearity mitigate to plus minus 0.5%. Then we tried another 2 reweighting schemes, random and linear one, just to see what's going on. Still the binary weighting beat all of them. This is the spectrum of the output, the ADC. The B is the spectrum of the binary weighted ADC, which has SNDR of 75, better than SNDR of 39, almost twice. We study the effect of BBT, basically, the process and temperature. As we can, the x-axis is the temperature, the y-axis is the nonlinearity, the deviation, and the z-axis is the distribution of the samples. We are interested in figure B. We can see that there is no severe effect on the ADC. There's another property which is programmability of the ADC. So there is, if you can see, the input can be applied to change the curves of input to output. Okay? This is another feature which can be explored in future. This paper has been published, nitrogate transaction on very large scale systems. So, Francis, thank you very much for listening. And we'll be happy to answer questions.
So we'll take one question on this one.
Thank you for your presentation. How do you select appropriate number of elements in your delay chain?
That's a pretty good question. So if you increase the number of elements, you will basically increase the number of hours, right? And there's another feature that if you increase the number of elements, you will decrease the K-VCO, which is the gain of VCO. So you have to wisely choose the number of. At the end, you have to choose between, we'll find out, between 18 to 20 differential, which gives you around 36 phases. That's very enough to get a pretty good ADC. So there is a trade-off. Thank you.
Okay, our next presenter is Ms. Al-Roomi. Apologies for that.
Hi everyone. This is just a humble presentation based on literature review. In this presentation, I'm going to mention some points like why do we need to forecast load, wind speed and power, and solar radiation and power. And from literature review, I will mention forecasting methods, each of them, and then trying to introduce an integrated load, wind, and solar forecasting program. So, the figure shows the main components of the power system, the generation side, the transmission and distribution part, and then the consumer side, which can be industrial, commercial, and residential. Despite a small fraction of loss in transmission lines, it is known that in power system, the amount of generated power has to be balanced with the load consumption by customers, by electricity consumers, and at the same time, we know that the electricity consumption changes second to second, minute to minute, day to day, seasonally and annually, and this creates a challenge to make the balance, the needed balance between the generation and the load consumption, which requires that we have accurate predictions about how much will be the electricity consumption at specific times. Another point is that renewable resources such as wind and solar powers are contributing increasingly to the total generation in the system. But the nature of solar and wind power the stochastic natural, because they are intermittent resources, creates another challenge, makes not sure about that the total amount of generation in order to make the balance with the electricity consumption. So these are main reasons for why do we need to have predictions or to forecast each of the load, the wind power and the solar power. Other important reasons for doing this is that electric companies need to do forecasts because it helps in good planning and making correct decisions regarding the future generation and transmission, the infrastructure. When we say the future, this future may mean seconds, maybe minutes, maybe day, week, and whatever. Doing the maintenance in planning or designing the infrastructure, and determining what resources needed for the future. It is stated in the literature that a small amount of accuracy in forecasting can help us saving a large number of millions of dollars can be saved by just a small increase in load forecasting accuracy. There are many forecasting methods and generally classified as statistical models, artificial intelligence-based models, and hybrid models. Two main parts of statistical models is a time series that depends on the past information of the variable that we are going to forecast, and another one is the autoregressive that the variable we are going to forecast depends on some other independent variables. The artificial intelligence-based models, they have ability to deal with complex and linear models, and then the hybrid models that combine two or more from individual forecasting models in order to take advantage of their strengths and to overcome others' weaknesses. So statistical and artificial neural networks have been widely used. However, an increased focus have now been directed towards hybrid and other intelligence approaches. So regarding load forecasting, it has been found in literature that a specific forecasting model depends on the time horizon and the amount of information available. Traditional methods cannot help us in load forecasting because of the nature and uncertainties of our system. So applying non-parametric, which is artificial intelligence-based techniques in load forecasting can overcome the limited capability of parametric statistical models. Neural network modeling have been found useful in forecasting loads when we have not enough information, and the optimal load forecasting when we are dealing with when our system contains solar power resources, wind power resources, and we are dealing with the load. So there is still a need to make more research in order to improve the accuracy of forecasting. This is a sample for the time horizon. So when we say the future, that may be short term, medium term, and long term, and they vary according to the time period, how long do we need to make our forecasts, and the purpose, why do we need to do our forecasts in this area. This is not firm. We may find different time horizons for the same thing that contain very short term, or we can find them different in specifying the time period. So regarding solar irradiance and power forecasting, we usually have the same techniques like the conventional and the artificial intelligence. Time series is not suitable in our case because of the nonlinearity of cloud. Artificial neural networks and support vector machines have been found efficient in this case. In addition, we have other two techniques that are based on satellite images and based on analyzing cloud movement using image processing. Regarding the wind speed and the power forecasting, the parametric or statistical models perform a challenge because of the nonlinearity of our system and high complexity of forecasting data. The artificial intelligence-based techniques they have more popularity and made it attractive to lead to suggesting different neural networks forecasting models. The hybrid models resulting from combining the previously mentioned two classes. This is an example for how it may be found different time horizons. We have the very short term, the medium term, the long term, with different time periods and maybe different purposes. So in case we have our forecasts for load, wind power and solar power, due to the variability of the renewable resources and the variability of the load, so we subtract the renewable generations from the amount of load, and then the result is to be, or the remaining amount is to be generated by the traditional generation. Yeah. So with the large amount of forecasting techniques used in forecasting load, wind power and solar power, there is still a need to achieve more accuracy, and it is still a subject of research, and the idea of this research is to try doing something different than the forecasting methods have been done separately, like each variable separately, and I'm thinking of doing integrated load, wind and power and solar power forecasting, depending on studying the statistical properties or distribution function of each of them, and trying to find a common distribution function that combines the solar power and the solar radiance and the wind speed, and to find the correlation between the load, the changeable, the variable load and these resources, and trying to think or to specify when to add the power generation from these resources and what will be obtained in the system. So, at the conclusion, there is a problem in the power system due to the variability of load from one side and uncertainty and the intermittent nature of wind speed and solar irradiance and the power obtained from them. Big research have been done, a lot of research have been done to obtain accurate forecasts and to improve the accuracy of different forecasting techniques, but there is still need to more accuracy of these forecasting methods. And it is expected that, or it may be useful to study or to to plan to make integrated solar, wind, and load forecasting together. Thank you.
So we'll take one question.
Thank you for your presentation. I couldn't understand what is the results.
As I said in the beginning, it's humble literature review, thinking of doing different methods of forecasting the load consumption and the renewable, the power generated from renewable resources such as wind and solar.
All right, so well done for everybody this morning. So that ends the morning presentations. At this point in time, I've got 11:50. There's going to be 1 hour for lunch. Lunch is going to be outside, but before everybody runs off, I need a couple of things. I need the validation forms. For those who have them, I'll take those back. And after this, as soon as you guys walk out, there's going to be a group photo. So go out, stand, get around, smile, get the photo done, and then we're off for lunch. Questions before we go? Okay. So we'll see everybody back here at 12:50.